Hi class, today we're going to do the normal distribution, so let's get started. So the normal distribution, we have a probability density function that looks like this. You don't need to know it, but it's the normal curve that goes like this, and we want to calculate probabilities with that normal curve. Examples are like temperature in this room or weights of manufactured parts, heights, SAT scores, many things follow a normal distribution. Look at the S&P returns. That's close to normal, not quite. To calculate normal distributions, we use the normal CDF from lower bound to upper bound. So normal CDF from -2 to 1.2 is equal to that. Try it. So let's calculate some of these. Say we wanted to find the probability that a z-score is between 1.2 and 2.3. Well, we just use normal CDF from 1.2 to 2.3 and we get this. Let's see it on the calculator. Okay, so how do we do that? Well, we can just go second distribution. We go down to normal CDF, so normal CDF. And we type in 1.2, comma, we hit the comma button and all the way to 2.3, close parenthesis, and enter, and we get 1.04. You can try it for this one. Say we wanted to find the probability that z was less than 0.6. Then basically we want to go from -infinity up to 0.6. And if it's normally distributed by the empirical rule, we know that 99.7% of the data lies within 3 standard deviations. So if we go out to a -8 standard deviations, that's close enough to infinity that you need. And why do I use 8? Well, it looks like infinity just raised up, right? You took infinity and rotated it up 90 degrees and you get an 8. So that looks like infinity. It's far enough out. You could put a -99 or negative, but either way you get to this 0.726, and let's see that on the calculator. So we use second distributions down to normal CDF, and we use the minus down here, -8, comma, to 0.6, close parenthesis, and we get our 0.726, rounding that up to 0.6. And you can try the rest of these, but that's how it's done. If you wanted to have a z-score of greater than 1.5, then you go 1.5 to infinity, and again we use 8, and we get this, and you can try these. Okay, so in real life we don't have a standard normal. By the way, standard normal is a normal distribution with a mean of 0 and a standard deviation of 1. So z-scores are standard normal distribution, so we just can convert. If we don't have a normal distribution, we just convert the values to z-scores. They are standard normal, and we can calculate the probabilities with that. Let's do an example. Say age at first marriage. It was reported that the first time of marriage is at 26 years. And if we assume it's normally distributed with a standard deviation of 4, then what is the probability of a person getting married after the age of 30? Well, we just have to convert that to a z-score. 30 minus the mean divided by the standard deviation is equal to 1. So after the age of 30 is 1 or more. So if we do normal CDF from 1 to 8, we get about 16%. What about before the age of 20? Well, you can calculate the z-score same way. We get a -1.5. So before the age of 20 would be lower. So from -infinity up to minus 1.5, so we get about 7%. Now we can go the other way. What age represents the 80th percentile for getting married? So we need to find the z-score for the 80th percentile, and we use an inverse normal of 0.8. Basically, we're going to have a normal curve, right? And we want the area where we have 0.8 on this side. The area over here is 0.8. So what z-score represents that? And we have to use the inverse normal on the calculator. Let me bring in the calculator. Okay, so we go to second distributions and roll down to 3 right here. Type in a 0.8, close parenthesis, and we get a z-score of 0.84. So we have 0.84. Now z is equal to x minus x bar over s. And we can solve that now for x. We multiply the s over here. So we get x minus x bar is equal to s times z. Or x is equal to x bar plus s times z. So we can plug that in. X bar was equal to 26. And then we have plus, the standard deviation is 4. And we get 0.84. And we multiply that out, and we get 29.4. That represents the age of the 80th percentile. Or second example of that is, SAT cutoff scores for a school. SAT scores have a mean of 500 and a standard deviation of 1. If a school wants to admit just the top 10%, what would their SAT cutoff score be? Well, top 10%, so that's 90th percentile. So z is equal to inverse norm of 0.9, so 1.2 at 8. So x minus x bar over s leads to this formula. So we plug in 500 for the mean, 1.28 for the z-score, and 100 for the standard deviation. And we get a cutoff score of 628. Now, z-scores are good for comparing apples and oranges. So let's do an example. Which is more extreme? An IQ score of 135 or a GMAT score of 740? And here's the means and standard deviations for those, and they're both normally distributed. So what are the probabilities, right? Well, for the IQ score, the z-score is 2.33. And so the probability of that or more extreme is 2.33 to infinity, and that's about 1%. What about GMAT scores? Well, the z-score is equal to 1.9. And so we can tell just by the z-score, since this is a more extreme z-score, that's more extreme or less likely. But what is the actual probability? Probability from 1.9 or more would be about 3%. So we can see that this one is in fact more extreme. Okay, well, I hope you found that useful and aids to your learning of this material. Cheers.